Hello, I'm David Chin, and this is Lab 2 Lines of Charge for Physics 2212. So this lab was intended to modify the point charge assumption previously made before and make it a line of charge model, as seen in this lab. Compared to the first lab, we divided the tapes into a multitude of charges instead of a single point charge, and used GlowScript as a computational model to simulate the forces and electric field. We assumed the point charge to be 6.7 times 10 to the negative 9 coulombs from the first lab, and the charge on each line of tape was 1.859 times 10 to the negative 8 coulombs. The two equations we mainly use are the force of gravity equation, which is negative g m1 m2 over r squared times the r direction vector, and Coulomb's law, which is the same thing but with charges instead. These equations are based on Newton's second law, as you can see F equals ma. And we also used Newton's second law as neither tape was accelerating, meaning that they had to exert equal force on each other, which you can see later in the calculations, where we set Fe equal to mg. And so here are the lab 1 values, the calculations of lab 1. As you can see, this is the point charge that we used earlier. And for lab 2 calculations, you can see that we use many of the same constants from lab 1, such as the mass, the length, the width, and the distance between the tapes. And to find the charge on this new line of charge in this lab, we do the equation Fe equals Fg, which is what I said earlier for Newton's second. But instead of the Fe equation, which is different from this, we use an equation that accounts for the line of charge, so you can see that the denominator is different. And so we found that the charge on the line of tape was 1.859 times 10 to the negative 8 coulombs instead. And so for the GlowScript model, we model that equation in GlowScript, and we find that these are the constants. We set gravity, we have k, and then we have the mass of one tape and the estimated net charge. And then we are here setting up the lines of charge in the electric field. As you can see, this is the electric field equation. We're using constants like magnitude of r hat, and here is kq over r squared times r hat, which is the electric field equation, and then here we're making that line of charge equation. So we're finding each magnitude of the charge using n, where n is the number of charges, as you can see later in the model. And you can see that same thing for mass as well. And so for part 3, we're doing superposition, which is we're finding the electric field and the electric force from each point charge. In this lab, we used 100 point charges, and so we're just finding the electric field and the electric force from each one of those 100 point charges, which is different from the last lab as we're not considering it as a single point charge anymore. And then finally, we're creating the vectors. We have the E scale, we have the FG scale, and you can see that FG is negative mg, and then the Fe, we can see that this Fe on top, and we have a different scale factor since the Fe and FG are slightly different. And then finally, we'll be able to show the magnitude of the vectors and then finish the function. So you can see that these two are the lines of charge, the tape, so that's 100, and that this is the gravitational force equation, the gravitational force vector, and this is the electric field vector. So you can see that it's pointing up and gravity is pointing down, meaning they equilibrate. They should equilibrate as the tapes are not moving, but there is some error which will be discussed later. But you can see that overall, this is the electric field pushing the tape up, along with the electric force, which pushes the tape up, and gravity drags it down, but there's no acceleration, so these forces equilibrate. And these are the two magnitudes that we found in the lab. So for assumptions and error, we do ignore error distance on moving object, as we only account for force gravity and force electric. If we were to account for error resistance, we would assume that force electric or force gravity would both be stronger, as error resistance does account for a pull on the tape. And we do not treat the long tape as if it was a point charge, as discussed earlier. And all the charge is not concentrated at the center of the long tape, as be able to find a multitude of charges and calculate the force electric per charge as seen in here in the superposition for GlowScript. And we do assume that each U-tape has about the same amount of charge, evenly distributed across the length of the tape, as you can see again in the superposition and the line of charge equation, where we find that Q over N for each point charge, meaning that we do assume that about each point charge is the same mass and the same charge, and that it is evenly distributed along the length of the tape. And finally, for the discussion, we have the point charge that we found in lab 1 is 6.7 times 10 to the negative 9 coulombs, and the charge on each line of tape being 1.859 times 10 to the negative 8 coulombs. And these estimates differ due to precision in these calculations, as in the first lab, we assumed that the tape was a point charge, which is pretty imprecise. But in this lab, we find a line of charge, and we find that the line of charge model is much more efficient, as it is similar to a real-world scenario, as real-world objects are not point charges, rather they are distributed across the line of charge. Thank you.